All right, so we'll get started. So, as previously stated, I'm Josh Bevan, currently just finished my master's program at University of Massachusetts Lowell, and I'll be incoming PhD student at Urbana-Champaign in Illinois. This was a joint project with Professor Willis, also at University of Massachusetts Lowell, in the Mechanical Engineering program. And so this talk is a high-order conservative Eulerian simulation method for vortex-dominated flows. So it's a long title, and I'll try to unpack what each of those pieces means in the context of this. And I'll skip through a fair number of these slides. They're meant to be illustrative if you go back and look through the talk, so there's extra content that I won't necessarily touch on in this talk. So we'll start off with an introduction in terms of the motivation and goals of the talk, and then we'll continue on and sort of go through the methodology and so forth. So the main goal of the project was development of a high-order solver, which if you're at the high-order section, hopefully you have an idea of what that means in terms of convergence properties. And it's specifically for a inviscid, incompressible flows, in this case vorticity dominated. The work was done in 2D, but could be extended to 3D. And so this consists of two pieces. One is a high-order advective solver, and it needs to be capable of what I call mixed order flux handling, and I'll explain that a little later on. But it also will need a high-order BO-sub-R evaluation routine, which again I'll touch on. Ultimately, contribution-wise, if it succeeds, which spoiler alert it did, we have a complete high-order method for velocity, vorticity, and viscid flow. I'll validate the solver and show that the underlying Eulerian vortex approach is appropriate. And we'll take a look at the convergence error in performance of the method in the solver. So motivation-wise, these are all sort of second-level motivations. If you think of sort of top-level physical motivation, imagine a situation where you have a vorticity-dominated flow. One would be wind turbine farms, where you have wind turbines upstream and downstream of each other. And as a matter of course, you have wake coming downstream off of upstream turbines. And now that wake could impinge upon those downstream turbines, and you might care about that for any number of reasons. It might be performance or efficiency, you're concerned about how the wake interacts, or it could be reliability, maybe you're setting up some sort of resonance in the structure and you're worried about fatigue concerns. So ultimately, how do you go about simulating this? So it's challenging because when you think about the multitude of scale in the problem, the characteristic length is the size of the wind turbine blade. But downstream wind turbines are 20 or 30 blade lengths away. So it's quite a bit of distance relatively. So when you try to simulate this, you want to make sure that you are capturing the important features of the flow and that you're not smearing them out because it's traveling quite a bit of distance. So if you're dissipative, you're going to have problems. Similarly, if you're not explicitly conserving the quantity of interest, in this case vorticity, then again, you may have simulation challenges there. So, if we had the world's most powerful computer times 1,000, we'd do DNS and who cares? But that's impractical for most of these situations. The vorticity velocity form was well suited for these kind of things, for inviscid and incompressible flows. Traditionally, when you look at vortex methods, they're dominated by Lagrangian techniques, which tend to be more natural in the sense that typically you have vortices that are flowing, and you can track them in a Lagrangian manner, and it's fairly natural. Problem is when you try to extend these to higher order, you start to run into problems. Primary is when you initially populate the domain with your Lagrangian point vortices, everything's nice and organized. But as the flow evolves, of course, you're getting things rotating and so forth. Point vortices get disorganized, and the organization of those point vortices is paramount to preserving the higher order characteristic of the method or solver. So typically in a Lagrangian technique, you then have to remesh. So you'll have to project these points onto a grid, make new organized point vortices, and just do this every time. So it seems a bit odd in that we're trying to take advantage of the Lagrangian stuff, but we end up having to do Eulerian stuff along the way. Eulerian approach avoids this disorganization because we don't have to track individual point vortices. We just have the vorticity spread across the domain, and it's captured on the grid. And this has been done successfully at low order by Brown and several others, and he used a finite volume approach. So it suggests that at the very least, an Eulerian approach is reasonable, so is it possible to extend this to high order, which is important for, again, capturing vortex structures. So the proposed method is an Eulerian representation of both the velocity and the vorticity, solving the PDE. Velocity evaluation is going to be done via a BO sub r kernel, and the vorticity advection is done via a line DG approach. And I'll explain later on why DG versus other potential discretization approaches. And then finally, a method aligns approach for time stepping via an explicit Runge-Kutta method. So at its core, we have Navier-Stokes. If you think about vorticity, the quantity omega there, it's just the curl of your velocity field. So if you were to plug this back into Navier-Stokes, you can recast it as a velocity vorticity form here, where you lump all viscous generation of vorticity into a source term there. And so there's three components. One is the time dynamic portion, and then one is transport of vorticity, and then the other is vortex stretching. So I'm not going to touch much on vortex stretching, because if you do it in 2D, it doesn't exist, which is a nice simplification early on. The other big advantage is you're explicitly conserving the vorticity, because it's one of the variables in your PDE. The other is when you consider these problems, the vorticity tends to be sparse in the domain. There's only certain regions where you have vorticity, and everywhere else is empty. If you're going about a normal Navier-Stokes approach, you'd have to simulate your entire domain. Whereas with a velocity vorticity approach, areas where there's no vorticity, clearly you don't simulate vorticity because there's none there. And furthermore, you don't need to calculate velocity there because there's no vorticity to worry about advecting. And the velocity is the most expensive portion typically in these kinds of approaches, so it's a big savings. So without the vortex stretching, then you just recover something that looks very similar to hyperbolic conservation law. So for incompressible flows, we can relate the vorticity and the velocity here. And so you could try to find velocity fields by solving the Poisson problem. Alternatively, you can invert this to get what's called the BO sub r integral, which is the approach taken here. So if you're trying to evaluate a particular point x star, you have some kernel function that you're convolving with your vorticity. So this is just something that's describing how it propagates spatially. And so this kernel here is the singular BO sub r kernel. It's notable that it's singular because if you look, imagine you had a target point that you'd like to evaluate your velocity that's coincident with a source point. This clearly blows up. Now, we know in reality that you're not having infinite velocities, so that's clearly non-physical from a physicality standpoint, but also from a numerical standpoint, the fact that it's singular presents numerical challenges. So there's a couple ways to try to work around this. Lagrangian techniques typically, again, you have the non-physicality where you could get velocities that just aren't realistic. So what they do is they desingularize it. When you think about it, if you have a point vortice, you basically have a Dirac delta function. And so what they do is they convolve this with some finite cutoff radius, and so you get a blob. So, heuristically, it makes sense in a Lagrangian technique. You have vortex blobs instead of vortex points moving around your domain. Eulerian-wise, however, we don't have vorticity at points. It's spatially variant across our domain. So what purpose does the desingularization serve? Well, in this case, it's just strictly practical. When we look at convergent properties, I mean, sure, the BO sub r kernel, if you did this analytically, it would converge to a value, but just because it converges analytically doesn't mean our numerical techniques are going to go along for the ride. Principally because most quadrature techniques assume that a polynomial basis is a good approximation for whatever we're trying to integrate. And in this case, because it's singular or nearly singular, it's not a good approximation. So you have to, the singularization serves to make it a little bit easier to approximate with a polynomial. But there's a trade-off to be thought about here. It's difficult to integrate numerically. So if we make a smaller cutoff radius, we have larger quadrature areas, right? If we have no cutoff radius, okay, it converges very, very slowly. We use a very large cutoff radius, well, suddenly now it's quite smooth, so our quadrature is wonderful, but we introduce a very large approximation error in that we're changing what our physical vorticity is to be something that's easy to integrate. So there's a balance to be struck on the cutoff radius, too small or too large, and you have problems. So you can sort of see this. On the left here is the BO sub r kernel involved with some arbitrary vorticity, In the middle is the interpolation of that, as is whatever 12th order interpolation or something like that. You can see clearly this is not that, and indeed if you compare the two, you have a fair bit of oscillation because the polynomial approximation fails to properly capture the singular or nearly singular values. So I mentioned DG as our approximation technique for advection. Why DG versus other techniques? When you go down the list, finite differences, you have problems where you are tied to larger stencils if you try and view things at higher order. Finite volumes are great in that you can extend the higher order, but again, you have stencil problems which then limit the geometric flexibility. Ideally, you could do this on unstructured grid. Finite elements, hey, you can do higher order unstructured grids, but it's not well posed for hyperbolic problems. So DG sort of strikes the balance between both of those in that you can have a higher order unstructured mesh that has a bunch of nice properties, and it also captures the hyperbolic nature. So ultimately, I'm not going to go through all the DG derivation because it's unnecessary, but there's a couple points I'll highlight that are relevant. So here we've taken our velocity vorticity form, we've stripped out the source term, and so we just have a generic conservation law here. And so we go about the usual DG techniques. We say, okay, it's approximation, so we put residual. We look at, try to make that residual orthogonal to some set of test functions. And so certainly it's important to properly implement these things, but for the purposes of the method, this is the standard way you would typically go about a DG technique. Ultimately, we get this thing here, which describes globally the evolution of our vorticity. So again, here's our vorticity here. So we have a numerical flux function. We have fluxes within the element as a stiffness, and then we have a mass matrix that couples things. So more DG stuff. So overall, I'm not going to go through all the steps, but we have, from this, we can assemble together a solver that breaks this into the two pieces. You have the velocity evaluation and you have the vorticity advection. And when you just simply time step through at that point with your ODE that you get from your method alliance approach. So there's a couple methodological choices I made in implementation that have some ramifications. Again, we're polynomial basis. Notably, we take a line DG approach for 2D and 3D. So what this means is rather than having 2D basis functions that describe our solution approximation, we actually construct it from a tensor product of 1D. So this is quite nice because now you just simply have two 1D problems that are coupled at the points that they intersect. This does obviously impose limitations in the sense that you're restricted to a tensor grid for your interpolation points, but for our purposes, that's not terribly restrictive. So then we break it down into our 1D pieces. So again, so we have this particular point that we look at the time evolution. It's simply the linear combination of the change to the stuff happening along the y direction and the x direction. Okay. So we touch on the mixed order stiffness integration. Basically, I'm not going to go into all the details, but we can put together a special set of quadrature weights for our numerical quadrature that allows us to have different orders for both our velocity and vorticity. This is useful because if, let's say we have a sixth order method, clearly we need, or we would expect to need, a sixth order interpolation for our vorticity, but do we need a sixth order velocity field? Can we get away with a fifth order or a fourth order? Being able to decouple those is awfully nice because then you can truly study the impact of the order of the velocity field on the overall method. If you can reduce the necessary velocity field, we save time computationally. So we'll skip through a bunch of this math. So our velocity evaluation then turns into this discrete thing, and it's essentially just the sum of the discrete Biot-Savart evaluation for all elements within the domain at a particular point. Of course, you need to do this for every single point. So if you take a naive approach, which was done here to eliminate additional confounding factors, it's an n-squared problem, so it can be expensive. But there are techniques that help solve that. You tree code methods and fast multiple methods that can be applied. In this case, I ignored doing those just because I didn't want to. Typically, you introduce some additional approximation error with those techniques, and I didn't want that to be a consideration with this. And because we're at 2D, it's still reasonable to run with direct summation. It's also interesting to note, because it's an n-squared problem, you have kernel values, and at each target point, you have kernel values for all the source points. But then you need to do that for all target points. So again, it's an n-squared problem. If you're to try to save all these kernel values, you're not going to have enough memory. Similarly, if you were to just recalculate them every time step, that's prohibitively expensive. So what you can do is sort of refer to a reference domain, and for a particular reference element within those certain target points, you can have all the source points for that reference element, and then you can map this to the global domain. So you don't have the computational expense of recalculating, but you trade it for a smaller cost in terms of memory overhead for indexing non-contiguous blocks of memory to retrieve these kernel values. And then at this point now we have our semi-discrete system, so we can go about time stepping. In this case, it's an explicit method. It's a relatively newer Runge-Kutta method that's slightly more efficient. It's about twice as cheap compared to canonical RK4. So at this point, we now have theoretically a solver that gives us answers. So the question is, how do we determine if it's correct? So I looked at 3 different validating cases. The first is the Perelman stationary vortex. This is just how it sounds. You have a circular vortex that's just rotating. The nice thing about this test case is it permits an analytical solution. So when we get values calculated from the solver, we can directly compare them against exact answer and be able to very easily see what our convergence and errors look like. So going back to the cutoff effects, we have to choose our radius intelligently. This first one here, this is for a smaller radius. You can see it starts out, this is for a 6th order method, so we're close to 6th order. This is the best initially, but then it starts to drop off, and similarly here. So, and then if you look at too large of a radius, we're nice and stable, and it actually starts to increase a little bit. This would asymptotically level off, but we're far below what optimal convergence is. So there's a happy medium to be struck. Now this behavior is because if you look at, this is for our vorticity error, if we look at our velocity error, the lines patterns match. So you can see the highest order convergence on velocity matches that happy medium for our vorticity. So what's going on is the ones that are initially higher order have lower approximation error because our cutoff radius is smaller. We're closer to that point vortex. But the velocity errors are larger. It's not a problem initially, but as the problem evolves, those velocity errors start to accumulate, and so we get a degradation of the overall performance. Here, it's nice and stable. Our velocity is well behaved, but we're producing so much approximation error that we reduce our overall order of convergence. And so if we look at for a couple different orders, we can see the overall convergence. So this is chosen for the best cutoff radius for each of these orders. You can see generally that odd order methods, you get optimal convergence, and in even order methods, you lose about half an order or so of convergence for the analytical test case. The first quantitative test case is one by Strand. In this case, you have 4 interacting vortex patches, varying strengths, varying locations, that all spin about each other. We don't have an analytical solution here, but what we can do is we can get coarse grids and find as best a fine grid as we can tolerate computing, and compare the coarse grids to the fine grids. The fine grid is going to be much closer to the exact solution than the coarse grid is, so it's a kind of a pseudo-exact answer that we can compare against. And so long as they're sufficiently far away, we recover something that is close enough to for quantitative purposes for comparison. So here I'm looking at 4th order method and a 6th order method for this. Again, cutoff radii I chose optimally. And you can see something odd. Well, first of all, clearly we're not getting 6th or 4th order. The other is that 4th order persists until where 6th order would happen time-wise, 4th order is. So there's something underlying here, either the physical problem or the underlying solver that's setting some sort of lower bound on what our allowed rate of convergence is here. Now, if you were to choose a, that's okay. So if you were to choose so the 6th order method, now you choose a larger cutoff radius. We're nowhere near 6th order, but at least it's stable when we get high order. So, you know, it's not 1st order, it's not 2nd order, but it's certainly not 6th order. So it's better than nothing, but it's not what we would like to see. And so here's a qualitative comparison. Top is Strand's results, bottom is from the present solver, and they increase in degrees of freedom as you go. You can see for this case, you know, like 3,000 degrees of freedom, it's almost as good as the best case with 25,600 degrees of freedom. So either we're converging faster, or we just have lower absolute error to begin with, but certainly it's an improvement over this was a Lagrangian technique. The third qualitative test case was by Koumoutsakis. In this case, we have an elliptical vortex patch. The thing that makes this an interesting case is typically when you have non-circular patches of vorticity, you allow them to evolve, they eventually axisymmetrize, they become circular. In this case, even carrying it out for, I think it's around 400-something dimensionless time, it stays elliptical. So it is a good test of the long-time performance of the solver, because if you're dissipative or you're not conserving vorticity, this is going to tend towards axisymmetrizing again. So if you can continue to persist in the elliptical nature of the vortex, then you're hopefully doing something right. So again, top is Koumoutsakis' work, below is results from the solver at the same time steps. And you can see it compares quite favorably with the results. Notably, there is some numerical artifacting in regions where there's high gradients of vorticity, and that's just the consequence of the polynomial basis. You're going to get slight oscillations in high gradient areas. And there's probably ways to mitigate that, but that wasn't investigated in this case. So the final feature of this is looking at the aspect ratio. This is essentially the overall aspect ratio of that elliptical vortex. You can see high aspect ratios starting out where it's more elliptical, and then it reaches a quasi-steady state where it's not really dropping down to symmetrical. And again, we favorably compare with Koumoutsakis' reported results. Notably, we get a little bit higher peaks than he did towards the end of the simulation. Maybe we're less dissipative, or maybe we're just wrong. It's difficult to say, but I mean, one would think if it seems less dissipative, that's a good thing. So we did these validation test cases. Everything looks good. Convergence rate, high order for the analytical case, high order for the qualitative test cases. So how do we go about fixing this? Well, rather than doing a desingularization technique, what if we were to try to attempt to integrate the Biot-Savart integral exactly? Now, certainly, if you just let the thing run for eternity, you can get the thing to integrate exactly, but you want something that's going to have reasonable runtime performance. So we look at velocity evaluation here. Of the exact vorticity, we get something like this. Notably, the variable portion of the interpolation here is outside the integral. So this is constant. Certainly, it varies with respect to each of the indices here, but you could pre-compute this slow as you want, because you can save the values, and then generate a set of modified quadrature values. Now this will, assuming you do this integration properly, this will be exactly integrate that Biot-Savart integral. So no approximation error and no quadrature error, or none beyond what you would normally get with quadrature. And so what does this mean? Well, if you were to divide by the usual Gauss-Legendre points, you recover essentially a modified kernel value. So this is something that looks far away, looks close to what normal Biot-Savart kernel values would be, but close to the singularity, they modify themselves to be consistent such that the integration is exact. So the question is, what do these kernel values look like? Well, if you plot them, the centerpiece is for a particular target point. So this is within the element, and these are adjacent elements along a coordinate direction. So you can see this is relative difference between the modified kernel values and the exact Biot-Savart kernel values. And beyond the adjacent element, it drops to essentially within machine precision. This is nice. It's local. So A, we have less calculation to do. We only have to do right around the region of the source point. And B, because it's local, that permits promising opportunities for things like fast multiple methods where you need compact support for the functions for the technique to work. So in conclusion, it works for the sake of brevity. it could work better. Hopefully, the exact integration techniques will point a way towards being able to be more successful in that endeavor. Now, I'll solicit questions, and while we're doing that, I'll also show some. This is the fun part, right? You got to see the pretty pictures. So this is the strain test case. So there's the 4 vortex patches, and as the thing evolves, you start to get filaments. This is the end of where strain looked at. I went a little farther just to see, did he choose a fortuitous point and it went to hell afterwards. It gets real stringy, but in this case, it still continues to persist. Those are very fine vortex structures to resolve. And then the Kumasakis is slightly less exciting in the sense that it just continues to do what it's going to do, which is just spin up and stay elliptical. Any questions?
Any question for Josh?
So you can see him. Yeah, sure.
So I'm actually like I just started studying the DVT and this is what it's particle method.
Mm-hmm.
Would you comment on like how your method kind of this because this uses vortex blocks, right? Kind of
it's not a Lagrangian technique; it's an Eulerian technique. So it's not really using blobs so much as I mean, you just have it's Eulerian, so you have your vorticity interpolation across the entire domain. The desingularization, unlike Lagrangian techniques, it doesn't really have a physical reality. You're just kind of using it as a means to an end to be able to have your quadrature do something reasonable. So it's perhaps smearing it or averaging it in some way if you're looking for a physical interpretation of that. But yeah.
And along those lines, if I may ask.
That's okay.
Sure.
So could you kind of elaborate on the role of like a free code or FMN?
Yeah. So when you're evaluating your velocity, it's by far the most expensive part of the computation because, especially if you're doing a direct summation technique, it's n squared.
Sure.
But even then, you're evaluating a lot of integrals, and you're doing that every time step. So a tree code or a fast multiple method, what that attempts to do is reduce the algorithmic complexity from n squared to n log n, or ideally n. Now, part of the question is, what's the constant in front of there? Because, you know, of course, it looks awfully nice in a paper, but when you go to make this thing run on the computer, if you have a billion in front of your linear time algorithm, it's not going to be practically useful. But in this case, because it's a Eulerian technique compared to a Lagrangian technique, you can pre-compute all those weights and values and store them. Whereas Lagrangian points are moving around, you're going to have to recompute, you know, your spherical harmonics or whatever the case may be. So it's awfully nice. So it's at first blush you think Lagrangian is the obvious technique, but then suddenly having all these advantages of an Eulerian technique where you can pre-compute these values gives you a lot of advantage.
Another quick one. Would it be possible to obtain the same kind of results with just a lower order scheme but with a much finer mesh? Or
sure.
Is it fixed order?
Yeah, so ideally your problem is perfectly smooth, right? It's infinitely differentiable, and then you're great. If it's third order smooth or something like that, using a 12th order method is probably not going to get you much other than just getting that interpolation a little bit closer. Ideally, you'd be doing an HP adaptive method on this. Areas where it's smooth, you just put P as high as you can. Areas where you have, like, for instance, on these filaments, if your element is this big, you're wasting a whole lot of that element on stuff that you don't care about. So if you could refine within filament areas, that would be helpful there. But certainly, yeah, I mean, there are advantages low order as well in the sense that when you look at the way I approach some of the mixed order stuff, you can use far fewer interpolation points than you'd expect for vorticity because I'm using Gauss-Legendre points for vorticity, but Lobato points for velocity. So at the edges where you have the fluxes, if you have a second order method and you have, or a first order method and you have the first order velocity field, you actually don't have any velocity interpolation points in there. You just have it on the edges. So it's quite good. But as you go higher up, then the Lobato gets you less and less in the sense that you're only saving a couple points if there's 20 points.
Great. So we run out of time. Let's thank Josh for his talk. So now the second speaker. So the second speaker comes from Stanford. I guess it's Dr. Piassas. He's from Professor Sanjeeva Lele's group.
Great. Okay. Thanks for the introduction. My name is Niranjan Desas. I'm a postdoc at the Center for Turbulence Research. Let me acknowledge my co-authors, Akshay Subramanian, who's a PhD student with Professor Lele and Professor Sanjeev Lele. Let me also acknowledge Dr. Andy Cook and Lawrence Livermore National Lab, who's funding this project. So our title is Elastic Plastic Flow in Solids, Coupling with Fluids, and High Order Eulerian Methods for that. So here are some examples of large deformation elastic plastic flow in solids. So here is a pressurized gas contained in a cylindrical cavity made up of copper. So this is a solid, and there is a gas inside. A converging shock is set up in the solid. The shock passes through the interface, bounces off the axis of symmetry, and then there is a reshock where it passes through the interface again, which gives rise to these nice finger-like structures in the solid gas problem here. Here is another problem. You have a metal sheet of finite thickness, and a projectile or a bullet impacts it obliquely and passes right through it. You have these ejecta of the metal flying off because of this bullet. These two are numerical simulations, recent simulations from other groups. Here is an experimental study where you have two dissimilar metals, titanium and copper in this case, that are impacted against each other at a very high velocity and at an oblique angle. You have plastic flow in the interfacial region, and that gives rise to these rollers, which look somewhat similar to what you would expect in fluid. So, these are some of the examples where we finally want to go. And if you look at what are the common features that occur in this, you have large, and by large we mean nonlinear and elastic and plastic deformations in solids. Then you have shocks propagating through solids, liquids, and gases. Then you have the possibility of turbulence in fluids, so you have a presence of a large number of scales. And then you need to be able to handle the gas, liquid, solid interfaces. So our aim is to be able to do all these properties using a high order method. If you look at previous studies, there are broadly two groups working on similar problems. One is based in Caltech, and they use a hybrid finite difference and Venus schemes, so they have the potential to do high order. Their multi-material formulation is a level set-based approach that is inherently non-conservative and first order. The other group is based in France. They have a series of papers starting from 2008 up to 2015 and beyond. They use a diffuse interface formulation, which allows you to do use global higher order schemes. However, the numerical methods that they use are first or up to second order Goldilocks methods. So in this talk, I'm only going to focus on the first two aspects, since we are sort of in the preliminary stages of this work. So we'll focus on handling large deformations of solids and shock capturing in solids, liquids, and gases. So with that, a quick outline. I'll talk about the Eulerian hyperelastic formulation. We'll talk about the shock capturing scheme that we use with our Eulerian formulation, and some verification and validation test problems. So how do we handle large deformations in solids? So there are several measures of strain, and the one that we use, following several papers beginning from the late 1980s, is this inverse deformation gradient tensor G. So you have two frames of reference. One is the Eulerian frame of reference, which is fixed in space, and you have a Lagrangian frame which moves with a body, or a material frame of reference. You take the derivative of capital X with small x, and you get the inverse deformation gradient tensor. There is another further assumption. The tensor G is decomposed into a plastic tensor and an elastic tensor. So you have G is GP times GE. And you can write down an equation governing this GE which is given here. So you have the unsteady term, you have a gradient term here, and on the right you have three terms. This accounts for the plasticity effects. It's the plastic source term, and there are two additional terms which are kind of numerical fixes. So the first one here is ensuring consistency with mass. So the deformations are mass preserving or volume preserving. The other one is a curl constraint. So you see that there is a curl of a tensor term here, and that is again crossed with U. The curl constraint just states that the inverse deformation gradient tensor is each row of the G tensor is a gradient. So it's being pointed out repeatedly in literature that it's particularly important to satisfy this curl constraint in order to get accurate simulations using the inverse deformation gradient tensor. So again, we've written out that equation in index notation here. So you have 9 equations here. We couple this system of 9 equations with the standard Euler equations, which are probably pretty well known in the fluid dynamics community. So we have the continuity equation, momentum equation, and the total energy equation. So you have this. So this whole system of 14 equations allows you to track large deformations in solids from an Eulerian fixed grid prism. One difference you would notice is instead of the pressure, you have the Cauchy stress, and you need to be able to close for closure of this system. You need to specify the Cauchy stress and the plastic source term here. And for that, we go to the hyperelastic theory, which essentially assumes that the internal energy can be written as a function of inverse deformation gradient tensor and entropy, which is denoted as eta here. So you can use several different equations of state. The one particular equation of state that we are using is a separable equation of state. It has two components. One is a hydrodynamic component, epsilon h, and an elastic or shear component, epsilon e. So there are three parameters here, gamma, p infinity, and mu. The important thing to note is this mu, which is the shear modulus. If you set that to 0, you get the stiffened gas equation of state. Further, if you set P infinity to 0 here, you get the ideal gas equation of state. So this equation of state allows you unified treatment of gases, liquids, and solids just by tuning just by specifying the three parameters gamma, P infinity, and mu. So this is the equation of state. We invoke the Cauchy-Wilhelm inequality, which just states that the entropy changes, or entropy can only increase because of your dissipative processes. That allows you to write down an expression for the Cauchy stress, which is an exact analytical expression in terms of the derivatives of the internal energy with the inverse deformation gradient tensor. The plastic source term is phenomenological, or it's a model, but it is still thermodynamically consistent, and that's written out here in terms of the inverse deformation gradient tensor and the deviatoric part of the Cauchy stress. A quick word about the multi-material formulation that we're working on as we go further. It requires solving volume fractions and mass fractions as well as species energies. And you end up with a system of 12 n plus 4 equations for n materials. The other important aspect that we want to focus on in this talk is how do you handle the possibility of discontinuities. So we use what is called the localized artificial or LAD scheme. So we have these Euler equations, and now they have been supplemented with two additional terms. One is the artificial shear stress term, and there is an artificial conductive flux. There are three coefficients involved in these two terms, C mu, C beta, and C kappa, which allow you to control the effect of the artificial terms. And the idea is that by adding these artificial conductivities and diffusivities, you smear out the discontinuities over a few points. So the numerical scheme that we use 10th order compact finite differences in space. We use 4th order Runge-Kutta time integration. For stability, we need to apply an 8th order conservative filter after each time step. And the LAD scheme that I just mentioned briefly It has three coefficients, C mu, C beta, and C kappa. C mu and C beta are artificial viscosity coefficients, and C kappa is an artificial conductivity, thermal conductivity coefficient. So this LAD scheme with these typical values for C mu, C beta, and C kappa has been well established previously. It's been shown to work pretty well for ideal gases. So we want to investigate how it extends to liquids and solids. So moving on to some simple problems that build up our method. We consider a plane strain problem. So you have a 1D, 1C solution of this form, where the inverse deformation gradient tensor G has only the 1 component as non-trivial. All other components are trivial. We assume the stress to be a Gaussian pulse centered at x equal to 0.5, moving to the right with a velocity Cn. And the sigma naught here controls the strength of the Gaussian pulse. So for sigma naught, for a very small value of sigma naught, you would expect that the linear solution is valid. So our entire formulation reduces to just a simple Hooke's law. And you would expect that a Gaussian pulse, which is initialized at x equal to 0.5, translates smoothly to the right. So for sigma naught equal to 10 power minus 5, we see that is exactly what happens. And the numerical and the analytical solution match pretty well. For sigma naught comparable to 1, in this case 0.1, we see that the pulse, which was again initialized at 0.5, has steepened considerably by the time it moves to 0.7 a short time later. So we can now substitute this assumed form of the solution into our governing equations and derive source terms that are needed to drive the solution to the desired solution. So this is the standard method of manufactured solutions. And once you include those source terms, we see that the numerically computed solution matches pretty well with the manufactured solution. So we can perform convergence tests based on this manufactured solution. And so here we are plotting the A2 norm of the error for different spatial resolutions. And we see that we get the desired 8th order convergence in space. Similarly, in time, we have the expected 4th order convergence. So these are different quantities. We have G11, or the 1 component of G, the non-trivial component of the tensor, U and velocity and pressure. So we have the desired 8th order in space and 4th order in time, based on for a smooth solution. So the next issue is shock capturing. So for that, we select the stationary normal shock problem as a canonical test problem. We begin with the shock jump relations. So these are continuity, momentum, and energy balance across a shock. The standard Rankine pneumonia conditions. We need to solve this problem for a specified choice of the pressure jump across the shock P2 by P1. So the problem is fully specified with this choice P2 by P1 and the equation of state parameters that I introduced previously. So gamma, P infinity, and mu. And we are going to perform tests on different materials. So we choose air, water, and steel with typical properties given in this reference. So one thing to point out is that there are a 3 order of magnitude difference in the density between air and water, and another sort of an order of magnitude jump between water and steam. And again, just to point out, gamma, P infinity, mu, all 3 are non-zero for a solid. For a liquid water, you have mu equal to non-zero, and these two parameters are, sorry, the shear modulus is non-zero, while these two are, the shear modulus is 0, these two are non-zero, while for a gas, both P infinity and mu are 0. So, with these initial tensions derived from solving this nonlinear problem, we perform simulations and we get a converged solution. So here we are plotting pressure versus x, or the pressure profile, with a jump at x equal to 0.5. And what we observe is you have Gibbs oscillations because of this discontinuity at x equal to 0.5. And the wiggles, the magnitude of the oscillations, or the magnitude of the wiggles, is a strong function of C beta. So for C beta equal to 1, we have a fairly large jump, of fairly large oscillations, while for C beta equal to 20, the oscillations are smoothed out and the shock is small. So we can quantify the amplitude of oscillations and plot that as a function of C beta, which is done here. And you can see that as you increase C beta, the amplitude of oscillations reduces. So, but of course, there's a trade-off between the amplitude and the shock thickness, because as you smear out the shock more and more, it is going to cover a larger number of grid points. And ideally, you want to capture a shock as crisply as possible. So as C beta increases, the shock thickness, which is on this axis here, it increases with C beta. So, so there is a trade-off that we need to be aware of when we select what is the correct value of C beta. And the question is the optimal value of C beta dependent on material properties and the shock strength. So this experiment was done on steel for a particular pressure jump. We repeat this for several different materials. So we do this for air, water, and these two are from the same previous experiment. And for several different pressure jumps. So for example, for steel, this figure is for 7,000, and you have similarly experiments at higher pressure jumps. And similarly for air and water, you have experiments at several different pressure jumps. So, so what this whole figure suggests is that the amplitude of oscillations is going to be a function of your C beta, the artificial viscosity coefficient, the pressure jump, as well as your equation of state parameters, gamma, p infinity, and mu. And that is somewhat worrying because that means that you need to change or tune C beta for each problem. It, however, turns out that you can couple, you can take this combination, gamma p infinity plus 4/3 mu, and that gives you a characteristic scale of pressure, P star. And if you plot your quantities as a function of P2 plus P star by P1 plus P star, you find that there is some sort of a collapse between different properties, between solids, liquids, and gases. So this suggests that the amplitude is going to be a function of C beta and this combination, P2 plus P star by P1 plus P star. So this considerably simplifies your problem. Your choice of C beta is much easier to determine based on this kind of a relationship. So in practice, we find that C beta, a fixed C beta of about 5 works pretty well for all the materials and gases and shock strengths that we've encountered. So that's the normal shock problem. We have a few more tests. The standard shock tube problem in air. So this is a classical test problem. The pressure jump of 10 and a density ratio of 8. We see that we have we don't have an analytical solution on top of this, but it agrees pretty well. Our result agrees pretty well. So you find some sensitivity to this parameter C kappa at the material discontinuity. If you look at a similar problem in steel, we have a much larger pressure jump now, 7 into 10 power 5, and there is no density jump across the initial interface. We again see that all the discontinuities are captured pretty well. The material discontinuity is, there are some oscillations, and they can be controlled by tuning the value of C kappa. Again, in practice, we find that values around 0.01 to 0.1 work pretty well. The last problem, sort of a verification problem, is this shock entropy problem. So we are able to capture shocks pretty accurately. We want to figure out what is the effect of the shock capturing scheme on a smooth solution. So we have a shock wave initialized at a certain location, x equal to 9.5, minus 9.5, and it is moving to the right. And there is an entropy wave downstream of the shock. So these are the initial conditions in terms of density, velocity, and pressure. At a later time, we find that the shock has moved somewhere here at, say, x equal to 8.2. This was the upstream entropy wave. And downstream of this, we find that we have a high frequency entropy wave and acoustic waves, which occur as a result of the interaction of this shock with this entropy wave. So we can compare the LED scheme our numerical method with several different numerical methods. And we use a ninth order Beano scheme with a very fine resolution as our reference. So what you observe in this, it's probably difficult to observe under this lighting, but you can see that there is a Beano 5 solution here, which consistently, which shows a significant reduction in magnitude. So the Beano 5 scheme is excessively dissipative compared to all the other schemes. So again, we are zooming into different regions here. So look, if you look at very close to the shock here, you find that the Beano 9 scheme has no oscillations compared to the reference. The LAD scheme with C beta equal to 1 and C beta equal to 2 have fairly large oscillations around the reference solution. Looking at this figure, you would think that the LAD scheme is performing bad. If you look at the post-shock region, you find that there is, again, Beano 5 is completely dissipated. Beano 9 has a significant dispersion error, so there is a significant phase shift with respect to the reference scheme. While the LAD schemes have much smaller phase shift. So the conclusion is that the effect of shock on the entropy wave is better captured by LAD schemes, although you have some oscillation. And if you're prepared to live with this level of oscillations, and you're able to control the oscillations and localize them to a region around the shock, you get a better resolution of the solution elsewhere. So let me quickly talk a bit about a few demonstration problems. So we have impact problems and no implosion problem. So here are two plates separated at x equal to 0.5. The plate on the right is directed to the left, and the plate on the left is directed to the right. So you're going to have an impact, and you will have shock waves traveling outwards in along both directions. So it displays animation. You can see there is a shock wave up front here, and there is a slower shock traveling behind this. So this is an elastic shock, and this is a plastic shock. So this is called an elastic precursor, and we have following plastic wave. So here we are comparing the velocity along the center line for different impact velocities, 100, 300, and 600. And we see that for 100, you don't have a following plastic shock. And for 300 and 600, you have this characteristic splitting, and you have an elastic precursor followed by a plastic shock. And again, our results compare well with the previous study. This is the only multi-material problem that we are demonstrating here. So instead of having identical plates on two sides, you have plates of different densities. So there is a density ratio of 2 initially to begin with. And what we see is a very similar qualitative picture, except that you have shocks of unequal strength and unequal speed of propagation traveling outwards. So this distance is different from this distance here. Also, you have a non-zero velocity at the interface. So the denser material or the high momentum material has overwhelmed the material with lower momentum. So this is another demonstration problem. Here we are plotting density contours inwards in an annular region between 5 and 50. And this kind of an initial condition gives rise to converging shocks and a diverging expansion wave. And the shock reflects, bounces off from the axis of symmetry, and interacts with the outward propagating waves. So we see that we have perfect symmetry, perfect cylindrical symmetry visually. And we also see that this method is convergent. So we are comparing 100, 200, and 400 square solution with a highly resolved cylindrical result. And we see that the Cartesian results approach the highly resolved cylindrical result. This is the last problem. So here is a schematic. This is a tangential no problem. So instead of having a radial velocity discontinuity, we have a tangential velocity discontinuity. So in a region, in a circular region of radius capital R, you give an initial solid body rotation. So U and V are specified as according to this. So this is a test case from a previous study. At t equal to 0 and t equal to 5, you have velocity and pressure contours, which are qualitatively similar in some sense to the radial flow problem. The reason for selecting this problem, or one important issue that comes out of this problem, is that we can determine how well the curl constraint that I talked about on the first slide is satisfied. So if you look at the tensor del cross G, and we take the 1,3 component of that, which is defined here, and plot the L2 norm of curl G throughout our entire domain as a function of your resolution, we find that the previous study goes down, the curl goes down as at first order, whereas using our high order numerical method, we clearly see 8th order conversions, and we're also fairly small at a fairly small level to begin with. So the curl constraint is satisfied much more accurately using our numerical method. So to summarize, we have an Eulerian formulation for elastic plastic deformations in hyperelastic materials, which covers solids, liquids, and gases. And we use a high order numerical scheme based on 10th order compact schemes and 4th order time stepping. Shock capturing is attained by using a localized artificial diffusivity scheme, and we've examined how well that extends from gases. And what we've tried to demonstrate is that we get good resolution properties in smooth regions, accurate capturing of shocks and discontinuities, and much better preservation of the curl constraint, which is important in solids. In terms of future work, we are working on extension of this to multimeter problems. So we'll be happy to take any questions.
Any question?
Me again. Could you elaborate on the dependency of the LAD method coefficients regarding with mesh? Do you know if it's sensitive to the mesh spacing or not?
So it's sensitive in the sense that if your shock or initial discontinuity is smoothed out over a few grid points.
More in the sense like, I understood that it has some sort of parameter tuning, right, to get the optimal performance of it. But does these optimal values are transferable, or can you use them on another set of meshes, perhaps another set of similar physical problems but with different properties?
Right. So it doesn't really depend on delta x. It depends on delta by delta x. Delta is the shock thickness. So if your shock has a physical thickness which remains constant across a problem, then you will need to.
It should carry over to the next set.
Another advantage is that this tries to localize the artificial terms to regions of discontinuities. So I didn't show the entire formulation of how we specify tau star and q star, but wherever the solution is smooth enough, the tau star and mu star, q star values go to 0, irrespective of the value of the coefficient in front. So it tries to localize it wherever it detects a sharp change in grade. Yeah. So if you were to make your solution or make your grid resolution finer, the tau star and the artificial terms will also.
Are there any other questions? Let's thank our presenter again. Next up, we have Cole Blakely and Ocean Kong from Utah State University. They're presenting on a higher-order Strand grid method for multi-species reaction flow. Cole is currently a PhD student there.
Been a while since I've been on a Windows.
We still technically have 2 minutes to take it down.
And they just click to go through again. Okay. All right, go ahead and get started. My name is Cole Blakely. That's the Sheen Cots in the corner there. And we're presenting high-order Strand grid methods for multi-species reacting flow. And I'm going to go ahead and start off with probably the least ubiquitous term on there, the Strand grids method. So those aren't super well known. Strand grids are basically generated by first creating a tessellated surface mesh along the solid objects you're interested in. And then from those, you project strands at the nodes normal to the surface. And then you essentially kind of copy and paste that surface mesh and basically go outwards along the strands, just going outwards like that. This is for basically a helicopter blade. And the goal is to have a really fine mesh density near the object so you can resolve really tiny features, especially good for turbulence. You can put it really in there in the laminar sublayer. And then to eventually work out to a coarser density to save on computational power. And at the very edge of the strands, you can either put a Barkle boundary condition if you're far enough away, or as in this case, you can mate with a Cartesian mesh. This is kind of a great hybrid that works with using the Strand grids to resolve the near body features and the Cartesian grid to resolve the off body vortical features and things of that nature. Some benefits to the Strand grids. They're really simple to generate, as was just outlined. These permit very high aspect ratios. Essentially, the way the solver works is it treats everything that happens in the tessellated surface mesh as its own 2D problem. And anything that's going along the strands, it treats that as basically a source term in those problems. So they're related, but it treats every single layer as its own 2D problem. We're allowed to do aspect ratios up to 10,000, which of course for traditional codes isn't allowed. These are also very adaptable. One of the primary goals of this original code is to work with a helicopter blade. And as you can imagine, you need a moving mesh. And as that blade moves, you can just create a new one on the fly. Saves a tremendous amount of time mesh generation. And these are also very scalable. If you can partition up your surface mesh, you basically already partitioned up your volume mesh as well. So that we've run up to 2048 cores, probably pretty common in this room, obviously. Now, the higher order method we're using is called flux correction. And this gives you third order accuracy without the need to compute second order derivatives. Here you basically have the flux between any two given points is the average of the right and left reconstructed flux minus the dissipation flux. That was right on my slide. I'm not sure why that got bumped up to here. But you can see the reconstructed fluxes are basically equal to the flux at point A plus half the distance between points A and B times a second order accurate derivative of the flux at A. Now again, that's only second order accurate, and notice we never computed a second derivative. However, when we do an integral along the boundaries of the element, we find that all second order error drops out. We're left with third order with a third order accurate scheme without again ever having computed a second order derivative. Sorry, a second derivative. All this means that we get third order accuracy with only a 30% increase in wall time from second order schemes. Now, also important to mention, this will make a lot more sense later in regards to multi-species reacting flow, is our source term treatment. Typically in a code, you have either a constant treatment of the source term in a given element or a linear treatment. This treatment here allows us to get third order accuracy within unstructured schemes, unstructured meshes. And the only downside is this one does require us to compute a second derivative, but that's only one part of the code. We still have tremendous savings in computational power with this method. Now, this is probably my favorite part, talking about the multi-species reacting model. I'll go into more detail about this later, but this is a laminar diffusion flame that is generating water. Now, the way multi-species reacting model work is the fluid is treated as a homogeneous mixture of components in any given element. For the number of species you need, so for instance, I'm going to talk specifically about methane combustion, which requires 5 species, you need 4 additional equations. Anytime you need the 5th element, you simply use conservation of mass, and you can deduce it's 1 minus the sum of all our mass species concentrations. And then because this is a reacting model, we have source terms, which cause consumption and production of species. That's presented by this omega dot right here. So this is the example of an additional equation you add to the Brand's equations. And yeah, so you basically have, for a 3D laminar solver, you have 5 plus these additional 4. As for the physics, the density is calculated via the ideal gas law. Obviously, it's going to be a mean molecular weight instead of the average molecular weight associated with air. The enthalpy is estimated to be a polynomial curve fits. For these temperature ranges, it is not safe to do constant specific heats. Transports are still, viscosity is still calculated by Sutherland's law. That's a pretty good high range. Thermal conductivity is determined by the relationship between viscosity and thermal conductivity by the Prandtl number. And the molecular diffusion is estimated by fixed loss, which is a very welcome approximation because it's very cost living-wise. Now, it's important to talk about the correction velocity that's implemented in this code. Once again, here's the additional equation we use for mass species concentration. If you sum this up for all 5 components of the flow and then subtract continuity, you are left with only this. Now, this equation right here, your diffusion coefficient of a given component in the mixture, there's no reason to assume this summation is 0. This is very empirical data, and because of the rules of mixture we've been using, this does not drop out. So what we do is we add this correction velocity here, which is defined here, and this causes the global mass conservation to be conserved. Otherwise, this looks like kind of a fictional cold fusion code. You get mass appearing and disappearing, so that's very good. Now for the chemical kinetics. One of my professors at Utah State said that our education there was the slow unraveling of lies. You know, you get every year and you look back on the year before and marvel at your naivete. This is kind of, I'm going to do a quick deviation from the truth to where we're actually at. So the ultimate is the elementary set. This basically has every single species and reaction that occurs in a given reaction, or a given process. So for even something as simple as combustion, you're in thousands of reactions and hundreds of species, and we don't even know all the elementary reactions out there. It's an ongoing research topic. The next set, which there's been considerable research into this, is a reduced set, where you basically remove everything that is negligible, that you can live without. Right now, there's one for methane, Green Met 3.0. It's 53 species, 325 reactions. Only the most simple 1D cases are usually attempted with this, because you would need 52 additional equations to your traditional set. Quasi-global 1D, this is probably the biggest jump between reduced set to quasi-global. This takes out everything you can and keeps just basic equilibrium relations and basically captures the absolute essence of what's happening. So for that one, you can do it with 4 reactions and only 7 species. There are some CFD codes that use it for quasi-global. All the codes for now, just due to our hardware constraint, we're using one-step global black box methods. This kind of is something that your high school, balancing equation, old stuff can kind of wrap its head around. Basically, the left side of the relation goes into a black box and out pops the other side. All humor aside, this is still valuable. When the proper Arrhenius rates are used, you can get good fits to experimental data for flame speeds, which are basically the rate at which a chemical will burn. So for certain CFD applications, this is still really valuable and still keeps you within reasonable computational expenses. For us, for our Arrhenius equations we're using, this is the equation right here. This is how you calculate your rate constant. It's basically your pre-exponential factor, your activation energy, ideal gas law, all those are, and also your temperature exponent, are completely empirically determined, and then it's an extremely strong function of temperature. This will change wildly between even hundreds of degrees. That rate constant is multiplied by your molar fractions, which are also raised to empirical exponents, and this gives you your rate of progress, the rate at which methane and oxygen are being consumed. So here is the relationship we've been using for this particular project. Now I have 3 cases I'm going to present. The first is the method of manufactured solutions. It's already been touched on by the speaker before me. Essentially, you select a random group of trigonometric functions, and obviously, if you plug those into the governing equations, they do not satisfy them. So to force them to be satisfied, you select a tailor-made source function that you add to the equation, so now that is your exact analytical solution. This is beneficial because you can compare true error, because you can compare it to your analytic solution, and verify your order of accuracy. So for this specific code, we were able to get third order accuracy for inviscid fluxes only, fifth order accuracy for purely viscous fluxes, and then third order accuracy when all terms were combined. Probably the most important thing that I want to talk about today are penalty-based boundary conditions. These are something that not everyone knows about, and they're very important. Essentially, to first make sense of them, you have to diagonalize the governing set of equations. Here, my gamma is my preconditioner. I do have a slide at the end. I didn't have time for it for this current presentation, but if there's any specific questions, we can go into it later. You have your preconditioner times your inviscid flux Jacobian times your primitive variables in this case, minus, again, the inverse of your preconditioner times your viscous fluxes. If you do an eigenvalue decomposition, your equation becomes the second equation. And if you multiply that by the left-hand eigenvectors, you're left with this diagonal set of equations. I'm so sorry. This really did work on my computer. I'm not sure what's happening here. But in this mindset, we can apply boundary conditions of this form, where alpha is a constant. Notice your eigenvalue matrix, I know it's a prime because it's going to be modified, and you have inviscid and viscous penalty data. Now, there are basically three things to keep in mind when you create a penalty-based boundary condition. The first is you want to enforce certain values. And you can enforce any value by using the correct linear combination of characteristic variables. If you sum them up right, you will get the thing you're trying to enforce. The second is you want to make sure this is well posed. That means you use the proper amount of linearly independent boundary conditions. For a traditional 3D RANS problem, you want to have 5 at an inlet and 4 at an outlet. And then the third thing you want to keep in mind is this bounded? And basically, if you add this equation to your diagonalized form, multiply by the transpose of your characteristic variables, you basically get this energy term, and you want to make sure that's bounded. And that's usually done by making sure you select an alpha large enough that it's below 0. That means it's bounded. Now, what's the motivation for this? These are often called weak boundary conditions as opposed to strong boundary conditions. A strong boundary condition, if you're at your boundary and say it's 310 Kelvin, you want to be 300 Kelvin, will come in and kick it down to 300, no questions asked. This will penalize it with a flux and will actually take its time getting there. It's much more stable. And for these higher order methods, these are very beneficial. So on to the second case. The second case is just a very simple one-dimensional inviscid channel, premixed flame. Basically a mixture of air and methane, again, already premixed, comes in, velocity of 10 meters per second, temperature 1500 Kelvin, and equivalence ratio 1.05. For those who don't know, the equivalence ratio is basically a measure of how much fuel there is to oxidizer. 1 corresponds to stoichiometric perfect. There will be no fuel or oxidizer left over. Below 1 means it's fuel lean. There's going to be a little oxidizer left over. This is a little fuel rich, so there's going to be just a little bit of methane left over, as we'll see. It's surrounded by 4 inviscid walls. Not to be confused, viscous terms still are there, so there's still thermal conductivity and things like that acting, and a pressure outlet of 101,000 pascals, kilopascals, or 101,000 pascals. Now, as for the inlet boundary condition, the modified eigenvalue matrix is basically, it is the exact same as a traditional Barfield boundary condition for an inlet, as is the inviscid penalty data. However, the viscous penalty data is very different. Typically, what's done here is you specify all viscous fluxes to be 0. Or another way of saying that is gradients are all 0 at this boundary. However, for the case of this one-dimensional reacting flow, we know the gradients will not be 0 at that boundary. They're going to be changing out of the gates, as we'll see. So instead, the viscous fluxes actually are used to further enforce a specified pressure and temperature, or sorry, not pressure, temperature, velocity, and mass fraction. As for the outlet boundary condition, we do have kind of a novel modified eigenvalue matrix here. I'm multiplying this by characteristic values to get a pressure back out, and your inviscid and viscous penalty data is identical to that of Barfield. Basically enforces 0 gradients at the outlet. The results of this are seen here. Gives you really good insight into kind of the structure of a flame. You have your oxidizer dropping to 0. You have your fuel has a little left over because again it's fuel rich. You're creating water and carbon dioxide. Your temperature spikes, as you can clearly see, and nitrogen is maintained just uniform. It's not changing. It's important to notice the scale on this. This is all happening at 0.4 millimeters. And again, this is moving at 10 meters per second. So picture you're in a car going about 20, hold out a ruler, and that's how fast this all occurs. So flame fronts can usually be pretty small. So now I saved the best for last. This is absolutely my favorite case. This is laminar diffusion flame over a horizontal plate. It's like your traditional boundary layer problem, but with explosions. And methane is basically injected through at a constant rate through a permeable surface. The inlet conditions are 0.5 meter per second, 300 Kelvin, oxygen mass fraction of 0.22. The outlet pressure is specified as 101,000 pascals. The permeable wall, now in terms of the eigenvalue matrix, it's identical to that of an immiscid wall. Its immiscid penalty data is slightly different. Typically what we do here is we enforce a normal velocity of 0. But because we have mass flow being injected, we do have a non-zero velocity that we're trying to enforce. So we actually try and enforce this normal velocity as opposed to the normal velocity of 0. And your viscous penalty data is particularly worth noting. This is basically, here again, is a non-slip boundary condition. Slightly different again because of the injected velocity. And then these last terms here are basically a mass and energy balance at this wall. They basically ensure that the amount of energy and mass that's being injected is equal to the sum of the inviscid and viscous flux at that wall. Yeah, so that's that distribution. That's how those penalty conditions work. The mesh layout, kind of a bit of a hyperbolic mess. You have an inviscid wall entry length followed by an impermeable wall, so this is the traditional viscous wall, followed by the permeable wall section. It's important to note how we basically caused ignition here. Obviously, if you just start this at 300 Kelvin and pump methane in, nothing happens. So this impermeable wall, upon convergence, which is going to be presented, has a 0 flux. It's an adiabatic condition. But during the ignition process, we actually pump in 40,000 watts per meter squared until the temperature is elevated enough, which causes ignition. Once the flame is formed, we then turn off that heat flux, setting it to 0, and because penalty methods take their time correcting it, the flame is maintained once the transient area has ended. So here are the fuel and oxidizer mass fractions, and this really well kind of describes how this is a diffusion flame. The first one was not limited by diffusion at all; it's eliminated by chemical kinetics. That was it. How fast can it burn? This one you can see here we have methane that's basically getting increasingly dense as you march down the plate. And you have oxygen that exists only away from the flame front. So in this area, there's no fuel. In this area, there's no oxidizer. And so you're only allowed to combust in this thin region right here, which is limited by your diffusion. So that's why it's diffusion flame. Sorry, this is the wrong title. This is your creation of your products, of your water and your H2O. Pretty similar. The diffusion rates are a little different. That's why they're slightly different. Here are your velocity and temperature profiles. Your velocity actually speeds up. Because of this tremendous heat release, you get a large temperature increase, a huge decrease in density. To make room, the flow must speed up. And your temperature as well kind of further shows you the flame front, this large elevation in temperature. Now, another one of my Utah State professors told me that CFD without validation is just video games. So here's our actual validation. Could be stronger to be certain. You can see here we are getting the acceleration they see in their data. We are accelerating more than they did, and we don't quite snap back at the same rate. And as for future work, the big thing this is missing is a grid refinement study. We have one in progress right now, and I'm happy to report that we have seen second order accuracy for the permeable section without combustion, so we're matching that to what we expect. Third order should be coming out soon, and then we'll run that with it without combustion. The other thing that we really want is an improved inlet boundary condition. In using basically something that's very far-field-esque, you must specify a pressure, which obviously you don't know in traditional combustion setup. You should have an unspecified pressure at that boundlet. at that inlet. And right now, we kind of have to do a guesstimate of what that should be and kind of check it to make sure it works out. So we'd like to have one where the characteristic equations specify only a velocity and temperature and mass species fraction. And then finally, we want to have a slot burner case that basically, it's like a Bunsen burner, but two-dimensional. And that will give us allow us to validate our flame speed and give us another way to check our order of accuracy. So I talked a little fast there, but that's it. Does anyone have any questions?
Yeah, I have one. Maybe they're not important, but do you model radiative heat transfer in this, or is it opaque, or?
No, ideally it should have radiative fluxes. They're at present not modeled, but yes, they can be very.
Now, how important are they? Are they a couple % of heat transfer? Are they like,
Depends
same
what
order of magnitude?
Depends what you're comparing to. For our temperatures, if you're looking at heat, it looks like it's pretty close. We're getting about 2100, which is what the experimental data says it should be. It's 100 degrees too hot. In terms of velocity, less so. I've read a couple papers where they say we're not using radiative heat flux. I know that doesn't mean it's okay, but they've gone close fits to experimental data. So it kind of depends on which variable you're looking at.
So then as a follow-up question, if you were to add radiative heat transfer, would that pose any problems in terms of the coupling the system? Because obviously then at that point you have speed of light versus the diffusive time for or conduction time for the heat transfer. Right. So suddenly the system is globally coupled, effectively, at least as far as flame propagation speed is concerned.
Yeah, I would hate to try and precondition the speed of light. That would be pretty brutal. I don't know. Toshi, do you know? Yeah, that's a great question.
Any other questions? Okay, well, thank you very much.
All right, thank you.
So we're running a little bit ahead. We'll start in 9 minutes or so. Fellas, if you want, you can start. See. Yeah.
No, you can sort of see that.
Has anybody seen Carlos recently? Was he here a couple months ago? So whenever you're ready. So we have up next we have I'll just butcher your last name, Carlos Eulerian, who is or recently graduated from the Technological Institute of Aeronautics. Also works as an engineer at Embraer, yeah.
Embraer, yes.
Embraer, as an engineer.
Super. Thank you, Jeff.
Thank you.
All right, so the title of the work is Complete Spectral Difference Methods Solutions of Compressible Flows Considering High Order Meshes. My name is Carlos Eulerian, and yeah, I know both are a mouthful, okay? So there we were in the lab having a meeting, all of us and my co-authors here, talking to ourselves. Well, okay, where they have a sufficiently developed high order spectral difference method solver for 2D Euler equations, where do we want to go? And I'm mostly the one to blame. So, oh, okay, so why not we have a high order mesh, a high order limiter, and also an implicit methods coupled with our high order solver. And eventually we found out that we threw more than we could bite. So hence a mouthful, okay? And these guys here are most of the first author. Fabio is the one that did most of the work, the implementation of the solver. Eduardo is the guy that worked with the implicit methods integration within the code. Andrea Aguiar is the one that worked with high order meshes representation. João is our advisor here in this group. So, okay. So as I told you, we are interested mostly on the institute, right? The institute, we have a CFD group that works with high-speed compressible flows, some sort of launch vehicles, re-entry vehicles, this kind of solution simulations. And okay, so why are you doing high order for these kind of problems? So the work here, this research is mostly for a simple constrained set of problems, right? But as in life, you have to start somewhere. So first to get your 1D high order solver going, get to know it very well. Okay, let's do the 2D now, Euler equations. Then you step up the game. Unfortunately, we've been in the 2D game for a while now. So as I told you earlier, all of these extra methods and schemes are necessary for you to have an effective high order solver. Okay, so as stated, you do need high order boundary representation to maintain the high order of the reconstruction. You also need, or you desire, for an implicit scheme to allow you to have faster computations and realistic analysis and performance. And you also, as the title said, if you want to deal with compressible flows, you want to have a limiter appropriate for these kind of methods. You don't want to rip off your high order reconstruction from the domain. Well, but back in the background, right? So our group worked with both Wino and spectral finite volume classes of methods, high order methods. These are mostly from the finite volume perspective. Previous work also, as I told you, we have a spectral difference for unstructured meshes, high order, but still considering a linear mesh representation, okay? And also a Redicata type scheme for time integration. And eventually, by this stepping up the game process, we said, okay, so let's try to tackle the viscous part of the problems, and let's find out what's really difficult about it. So this was a rather innocent look at first, but what I'm trying to share you this afternoon is that, okay, so despite being 2D, despite being well-known methods and methodologies, the coming together of all of these schemes and methods is it's harder. There's more than meets the eye in these topics, okay? So the objective was to verify the implementation, sure. course, we want to know if we are actually obtaining high order from the reconstruction. When you couple with the implicit schemes, it's should be fairly easy. And the high order mesh representation, the ability for you to solve your problems with curved meshes, is also another thing that is rather simple to do, to think about it, but it's harder, elaborate implementation, and you have so many corner cases that you must consider. Also test the viscous flow formulation, and eventually take a look into the transient test phase. So the solver formulation is a compressible 2D Navier-Stokes solver. Handles quadrilateral unstructured meshes up to fourth order reconstruction, actually. The Eulerian implicit scheme we chose for the linear C solution was the GMRS algorithm. The row scheme is used for numerical flux computation. And as for the limiting of the solution, high order solution, you use a hierarchical moment limiter. So I don't want to go too deep into details here, but the formulation of this factor difference actually bears more resemblance to the finite difference class of methods. You first map your cells of your computational domain to a standard element, then you have these separations here for a second or a third order scheme. A quadratic reconstruction, you need more degrees of freedom inside your cell, so you populate it with Lagrange or other type of Legendre points here, for instance. And you have two sets of degrees here. You either have the solution points and the flux points that lies on the boundaries also internally. With this set, you can create your desired order of polynomial, your desired reconstruction polynomial. And you do, for the flux point, you need an additional node so that you go one order higher, so that when you perform spatial derivatives, it remains the order of your method. Yep. The viscous formulation, we are using the internal penalty formulation. It basically depends on the property of both neighbors of a given cell interface, and also on their gradients. The implicit scheme here we considered, as I told you, was the GMRS algorithm. You essentially linearize this part of the equation, then you have your right-hand side that equals to the residue of your problem, your equations, and you step up here. So we consider this work a maximum number of sub-iterations for the linear solver solution, about 250. The Krylov subspace size of 30 is considered for the implicit simulations here, and about 100 for the viscous ones. For the case, I'll show some results here. We've considered a relative convergence rate of a drop of 5 orders in the residue of the linear system. And we use the PATC library for this particular work here. Furthermore, in details in the implicit formulation. So as a preconditioner, we use the incomplete lower upper factorization with 0 fill-in. It's actually part of the library. You just use it as a parameter for your library calls. And what was kind of different and was new in the sense that we had to research and figure out nice values was how to obtain a nice CFL growth law, or how to achieve the fastest possible convergence rate. And it turned out to be fairly straightforward for the viscous problems, but the viscous one we had to fine-tune many parameters and figure out what was actually going to work for some scenarios. So in the viscous one, you start also at about a iteration, for a fixed iteration of number 10 that we chose, you start to ramp up the value of CFL number. We saw that by doubling it at each iteration, eventually has no stiffness problem in your linear solver, no convergence problems. There are some problems reached that we could go up to nearly 10 to the 10th with a value that had no numerical problems for us. However, in the viscous side, as I told you, when we step, okay, let's just apply this for this guy here. Well, blows up in our face pretty early. So, okay, let's try to fix given a fixed limited CFL value up to a higher iteration number, then start to grow it slowly at each iteration, and decrease. And whenever the system converges the linear system, then you increase it. Otherwise, you just keep it the same for the next iteration. But eventually, found out that there is a stronger coupling of the CFL max CFL number you can reach related to the problem you're tackling. Yeah, we use a numerical formulation to compute the flux Jacobians. And that was mostly of the implicit parts of the work. And the next was actually mostly empirical work. You had to figure out what would work with the problems or not. Then we came to the second phase of this problem, this research. Okay, so how about the high order meshes? Let me skip the next one, then I'll go back. So here to the right, you have a quadratic mesh, okay, that's composed of quadratic quadrilaterals here. You have these, each solid dot here is actually a node that composes the element geometry. On the top here, you have your regular first order or linear mesh over a zoom region of the leading edge of an AIAA 0012 airfoil. So you also have the solid dots here, the nodes, that also exist on the other mesh, but this one only have the corner of the elements. And if you use such a coarse mesh for a regular CFD simulation, you will eventually not be solving or resolving your proper geometry. You have these linear facets here. When you go to the quadratic mesh quadratic mesh or high order mesh representation, some of the intermediate nodes that lie between the corners of the face, they are projected onto the elliptical or the CAD surface over there. So it better represents the same geometry but with a much coarser mesh. And if you want to do high order simulations in a timely fashion, you don't want to simply refine your mesh only to correctly discretize your geometry. You want to use the most possible coarse mesh to achieve faster convergence times. So this is, oh, yeah. So there are several approaches you can do to tackle this problem of how do you get a quadratic mesh over a general geometry. Our approach here in this work was to, okay, you start with a linear mesh representation, use commercial mesh generators or open source ones over your airfoil. And once you have that kind of mesh, then you kind of make a pre-processing step in your simulation to generate a linear one, a quadratic one based off the linear one. This guarantees that the linear mesh nodes are actually on the geometry, so that's the mesh generation problem. Mesh generation software problem. Our problem now was, okay, how do I project these middle face nodes onto the actual geometry? You have plenty of options, but one that would work generally for different kind of geometries was not directly available. So we chose to read the definition of a CAD geometry based on an IGES file, okay, and by reading the data in the CAD file, we reconstruct the geometry either with a B-spline or an orbit surface, and then within that in hand or in memory, we can correlate with the middle node of the face, then we project it. Right? So it's basically what I got over here. So besides the edges that lie within the boundary of the domain, you also add the middle node of the domain, the one at each edge of the cells throughout your whole domain. Okay. One problem, for instance, is, okay, what if I have a viscous computation, a turbulent flow that I have a boundary layer here developing? Eventually, I want to come to shorten the distance of this first node off the wall. And you can realize that eventually, if I come too close, these curved representation might cross over the other cell. And yes, that is true, and that's kind of an open problem for the high order forum here. And we're dealing with this problem as I speak. But for this particular research, we have considered that the Reynolds number value is low enough that we don't require too much cells with the high aspect ratio. So just in the sense to realize the importance of this topic of the high order mesh, we performed a simulation around a viscous cylinder with a Mach number of 0.2 and with this set of grids, okay? These are fairly simple ones to create, so you have a 16 by 16 and double it up to this one, finer mesh here. The far field is located at about 8 diameters of the initial cylinder position. And yeah, the same plot here is shown. So for the linear mesh, you have the edge is quite visible, different from the geometry, and for the high order one, you see that it projects much better. And so a little bit of nomenclature here. So Q1 stands for a linear mesh, okay, first order degree mesh, with a second degree polynomial for flux reconstruction solution. So it's a third order scheme using a first order mesh, okay? A mesh is with straight edges. And this other guy here is the same third order scheme, spectral difference scheme, however using a quadratic mesh. Okay, the one I showed on the previous slide that is curved along the edges of the boundary. So by simply changing the mesh, and this is for the coarser one, okay, you can see that the flow detaches from the geometry. And this is purely numeric, okay, or rather induced by numerical errors due to the mesh representation. What eventually happens is you can notice that there's a somewhat sharp transition for the angle is quite large, but you can still see, or actually the solver sees the normal units here on this face are quite different from this cell perspective from this other one. So what the flow eventually comes with is, oh, there's a discontinuity here in the geometry. So that leads to separation. These both are in the same color map, it's a Mach contours. Okay. The same kind of figure can be shown, or the same kind of rationale can be used for a second set of mesh, 32 by 32. And if I go back here, you can see that the resolution is improved due to the mesh. But also on this guy here, the resolution is also improved, but for the wrong physics, okay, totally induced by the geometry. And on our finer grid, 6.4 by 6.4, the same is observed again. So what I'm trying to come across here is, in this sort of high order space, it's no use to have a linear mesh, or it's of limited use, perhaps. It's a better term. Because sometimes we may be getting some results that are not physical, and they totally don't depend on the math or the solver formulation. It's strictly a mesh dependency problem. So this is sort of a requirement for this kind of solutions. And now for this result set here, for instance, one of the objectives was, okay, I want to have a high order solver. I want to know if we are getting high order. So not what's the point. I consider here the ring level flow problem is one with an analytical solution that I can compute the error related to my numerical one and compute the order of the method. So for this one, we use several different type of meshes, different level of refinements, okay? So what I'm showing here, the initial mesh here is just half of the domain, okay? But the initial mesh here is just really coarse like that. And these several other ones are simply visualizations of the spectral difference elements, okay? So this is not part of the actual visualization process. The solver has the various solution and flux points that I simply plot here to aid in the visualization step. So, okay, I'm doing better by going hard order here. It's a Mach contour plot. And this was the consequence of it by using the GMRS solver. You're also converging pretty fast in this case. As a side note, the last aviation conference, we had the same problem going over these ring-left flow computing orders. We were all good. However, this plot here, it would take up to about 1 million iteration with this split time step, about 6 hours. All of these solved in a couple of seconds. Okay, so this was a big step forward for us. And here is actually the plot of the error versus mesh refining here in the other axis. It's a metric for how fine your mesh is or how many degrees of freedom you have in your domain. So for the various orders, we are actually getting pretty close to what we were supposed to be. And, okay, that's good. Then a similar literature test case, the quiet flow, one that you can test your viscous flow formulation. Again, we used an initial force mesh, and the plot here is for the third order scheme, but just for visualization. So the boundary conditions are, there are different temperatures here in the lower plate and upper plate. You can also compute an analytical solution, as I said. Once again, it's a well-behaved problem. You can converge pretty fast with it, practically to machine zero here. This one also we used an infinite CFL value. And the order of this scheme is pretty much what we would expect. So, okay, as I said in the beginning, we're interested in compressible flows or aeronautical problems, so why not the trustful NACA 0012? So this is a subsonic flow condition, Mach 0.6, with no angle of attack. And yeah, this remark is here, this is one kind of problem that's been investigated in the high order workshop from AIAA also. However, for this problem, we use our custom meshes that we generated with custom tools. We also modified the NACA equation to perform a collapsed trailing edge for the geometry. It looks like this. So this is a plot of linear mesh. Okay, so if you zoom up enough, you'll see that the leading edge is composed of straight edges. And this, again, is an iteration about 5 minutes to reach matching zero here. And this shows using different meshes, either linear or a quadratic one with a second and third order scheme. Okay, these just density contours. It's hard to distinguish the naked eye what's different between one another, but you can see the entropy error is a log scale, right? So the Q1 mesh, the black line, actually has a higher entropy error than compared to the quadratic mesh. So as I said, by going with also high order mesh representation, you also are better resolving, or if it's a smaller error in entropy, which for an Euler case should be zero, so and subsonic one. And this one you have to hear both sides of the argument, make your opinion. What I like about science is this. You simply look at that and, man, it's wrong. Okay? So here's the same plot. What is different between the curves is the mesh. So what happens here? Each of these seesaw pattern here, I have plotted the boundary values at the actual boundary of the airport. Okay? So at about three nodes, I have, for inside of each cell, I have this pattern. Okay, so we're having a third order scheme, a quadratic reconstruction, so you can almost see the parabolas here inside an element. And when you use linear meshes, remember that I said that you mostly see, or what the flow would see, would be straight edges with sharp corners. That's the kind of thing we're seeing here. It sees some sort of expansion of the flow, right, besides the mesh connectivity. When you go up to a quadratic mesh, also with a third order or quadratic reconstruction, you no longer see that fact. So when you average the results, that's usually what we have, the post-processing tools that simply, okay, you have these 3 nodes, average them and plot your CP, you will not see the seesaw pattern. But when you plot the actual polynomial that's represent the solution within the boundary, then you can see this problem. And this is for a subsonic case. Another one for the RAE 2822 problem here is a much higher Mach number. Same concept of mesh. This one problem here is mostly how to deal with discontinuities in your solution, like shock waves here. So you can see that we're dealing not very well, I'd say. But this, eventually, what this plot is showing here is what's blue is high order, is unlimited by your numerical scheme, and the red cells are the ones that are limited for pressure reconstruction. So you can see that's somewhat here in the shock position, perhaps here on the high curvature geometry, but this still needs work. Okay, we're eventually able to compute this solution, but the hierarchical moment limiter has some shortcomings as we start to look into it. Nonetheless, we have a CL plot versus convergence, and this is for a explicit time marching scheme. So you see that it goes all the way up to 100,000 iterations. Eventually, you come by to close to a convergence in lift, right? It's close to the experimental value, but you still have too much oscillations over there. This is a SUP plot along with other high order methods. So this one we consider is the red one. It's fairly close to the experimental one, but this also is simply an inviscid simulation. It does not take into account the viscous boundary layer for this problem. So you would expect it to be act of the shock. This case here is a shorter Mach number of 0.5 and Reynolds 2500 here. It's a much coarser mesh, but the intent was to see a quadratic mesh resolution. Also, by this using the same algorithm now, the implicit GMRS solver, but with a CFL restriction of 0.8. That was as high as we could go. And this again looks wrong to me, but we're kind of investigating this problem now. Eventually, it reaches convergence or machine zero, but the rate is taking way too long. Okay, flat plate also to validate our viscous implementation. It's doing better as we increase the mesh definition. This is for a second order spectral difference solution. Okay, so we're just comparing the mesh refinement level with the analytical solution. So as you'd expect, as you increase the mesh density, even the second order scheme is able to compute fairly close to the analytical one. So some concluding remarks. The current implementation indeed shows high order reconstruction values. The viscous implicit capability is incorporated within the tool. It was not as easy as we previously thought it would be, but investigating many open problems yet. A high order mesh framework based on a CAD reader is also available, so this might be very useful when you go 3D. And the limiter seems to be sensitive to mesh quality, and there's groundwork for expansion and further improvements then. This was the future work in our past conference here, so it's just to say that to acknowledge my co-authors that they did an excellent work on going through getting the viscous one. You know, like I said, oh, this is promise for the next work. So he's showing the promise for the guys. So they did the viscous close, they improved the convergence rate for many of the problems, and they also are figuring out the limiter issues. Well, that's it, guys. Thank you very much.
So we have time for perhaps 1 or 2 questions.
Sure.
So you're having an implicit solver.
Yes, and then we also have the shock wave.
Do we expect that we're gonna have good convergence?
Well, I would expect it should be improved regarding to the split time scheme, but fully convergence to machine zero, that is not a goal for this. That's why in one of the plot sites we try to track the CL evolution along the iterations to see if we get something like that. In the Euler case that I've shown here, shock it typically stays in the same cell, or the marker for the limiter stays in the relatively same position. However, when you add the viscous effects, I would not expect that. I would expect it to transition or to move along the iterations. But
So it seems to me that when you have shock wave, then the number of iterations grows. So basically, you don't have a scale of it. So
yeah, that's kind of a much larger can of worms. Okay. Sometimes we have some indication that it would need to go HP adaptation, or perhaps multigrid, algebraic or geometric, to try to tackle some of these issues.
I would say that it doesn't seem to me that it will work because of the shock wave. If you have a smooth solution, then you could build the most optimal one.
Yeah.
But with the shock, I'm not sure.
Oh, yeah, this is the thing. We're open to to feedbacks, and research continues. I mean, it's an open problem for the whole community. So.
Thank you. So next up we have Professor Shabazi from the South Dakota School of Mines and Technology. Previously, he was a postdoc at Brown and University of Wyoming after getting his PhD at University of Toronto.
Yeah, I just want to reposition a little so you can see the screen more. There we go.
Close these. You put everything on this file. Or however. So, good afternoon, everybody. I'm going to talk about high-order hybrid Fourier continuation Reno scheme for 3D Navier-Stokes, compressible Navier-Stokes equation. So let me talk about numerical method for hyperbolic conservation laws. So our requirement is that we need to satisfy certain physical constraints. You want to be non-oscillatory. You want to have real as opposed to complex characteristic of speed, positivity of various quantities, okay? And also we had a talk that they were talking about the boundary conditions, so we have to also take care of boundary condition, okay? But also, we want to require, they have to be highly efficient to be able to compute practical problem of interest like turbulence, multi-phase flow, etc. So what I'm going to focus now on the efficiency of numerical methods. So if you look at first order method like Godunov's or Lax-Friedrich's, you can easily make them satisfy those physical properties. That means non-oscillatory, positivity, okay? But they're not very efficient. In fact, they're pretty poor in terms of efficiency. So let's show that for non-smooth problem. So here we had a bubble. That's a bubble of helium sitting in a body of air. Okay, so certainly we got non-smoothness. Okay, because the property changes, the density changes by a factor of 5 when you go from air to helium. And even gamma changes, goes from 1.4 to 1.67, okay? And we have that bubble interacting with the shock wave. Okay, so here on the right-hand side, you got fifth order method, the number of cells, 460. Okay, so this left-hand side, the solution, you can see the instabilities at the interface, they matches other published data. Okay, let's take that as our good solution, defined solution. Okay, on the right-hand side, you see first order method with 460 cells. So it doesn't even look like what we have for the same resolution, but fifth order. But in the middle, we got fifth order, but fourfold smaller number of cells, which closer to the defined fifth order method. Okay. We measure the error also. We take that as our reference and compare our solution to this. And you clearly see that the first order method, the fifth order method is superior. Okay. And more importantly, the CPU time. Look at the CPU time for the first order method is 20 times higher and still not as accurate. So we expect 2 order of magnitude improvement at least when you go to high order method. And these are the problems that are not as smooth. So now the problem with high order method is that when you're dealing with shock wave or discontinuity in general, they have to be nonlinear, and that nonlinearity cost us a factor of 10 roughly compared to the linear method. So what we are proposing, and there are several research groups that are proposing that using hybrid methods, high order hybrid methods, okay, which I'm going to talk about. So let's say that our governing equation, the Navier-Stokes equation, in 3D in indices notation, and we have two derivatives, derivative of convective fluxes, the second term from left, and then you have a derivative of viscous fluxes. So we have to be careful about how we treat the derivative of convective fluxes. So what we are proposing for our hybrid method, we say that if the solution is smooth, let's use a linear method, and in particular, the linear method is a Fourier, a variation of Fourier method. We call it Fourier continuation method, okay? And that's by Bruno and Lyon. Okay. And then for the discontinuous region, we're using Wino method, weighted essentially non-oscillatory method. And so I'm not going to talk about Wino method as it's the popular method. So let's talk about the Fourier continuation method and see how it works. So let's say that you have a function that is smooth, but it's not periodic. So the solid curve that we see here is defined from 0 to 1 and is not periodic. Okay? So if you use just the Fourier method, what do you get? You get an oscillation, yeah? So oscillation down, there's a Gibbs phenomenon, okay? Because it's a discontinuity. So the solution that John Boyd and Oscar Bruno, they came up with, and I guess in some other context, there were a few other people too, is that instead of looking at the original domain, let's consider a larger domain, okay, and approximate the original function fx with f tilde with a Fourier expansion over larger domain, okay, but make sure that that f tilde approximate the original function on the original domain very closely with high order accuracy, okay? That means that if you have the solution let's say if you have fx at an equal-space grid point, let's say k going from 0 to n, so you got n point data, okay? You make sure that that sum become fxk for all k, okay? Now, if you start approximating the, calculating these AJs and form that sum, you start to notice that if you want to get an accurate solution, the number of nodes that you need has to be larger than the number of modes, the Fourier mode. So the system that you're getting here to solve is an overdetermined system, okay? So you got what? You got less unknown than number of equation you have, okay? How are you going to solve that? The least square method via singular value decomposition. So you need to solve a system, and it's a singular value. You typically use singular value decomposition. Now the problem is that singular value decomposition is very expensive. So if you have n number of points, let's say in one direction, x direction, you got an order of n to the power 3. Okay, so in 3D, we're talking about n to the power 9. So really expensive. So now here is the trick. So if you want to do a smooth extension of the function, you don't need to use the whole domain. You only need to use the information from the point near the boundary. Okay. So here is if this is my function, yeah, I only need to look at some delta region near the boundary and use the information from there to construct the extension. Okay, periodic extension. Okay, and that is even though the number of points, if this region becomes smaller, still I have to use singular value decomposition, which is still not going to give me the complexity of Fourier method. Okay, how are we going to do it? This is what Oscar, Bruno, and Lai they came up with, was that let's find the extension of polynomials, some basis function like gram polynomials, okay? Let's do that for gram polynomials of whatever order, then compute the extension and store them once, okay? And now any given function, we're going to project it into the space of gram polynomial and reconstruct our extension. So this way we can achieve the complexity of Fourier method. The coefficient, so it's linear, the coefficient is slightly larger than classical Fourier method, but we get a linear complexity. Now we've shown in a couple of our papers that you can get fifth order Fourier continuation method even for non-periodic boundary condition like Dirichlet boundary. Okay, and the advantage is that you get almost dispersion-less and dissipation-less method. So if the solution have increasingly smaller scale, higher wave numbers, then the number of points to resolve that wave number doesn't increase as you increase the wave number, which for finite difference method, if you increase the number of if you increase the scale, make it smaller, then you need to increase the number of grid that you have. So now we have to have a mechanism to switch between Wiener method and FC method, Fourier continuation method, based on the smoothness of the problem. So what we use the multi-resolution method of Harton. There are several ways of doing it. For us, this so far, this multi-resolution method leads to a good shock detection and is very inexpensive. So our code is parallel, so we divide the domain into subdomains, okay, and we run the shock detection on each subdomain to figure out whether it's smooth or not. So if it's a smooth, it's FC method. If it's discontinuous, Reno method, okay. And here you can see the stencil. So FC method requires some data from neighboring cell, and this is, yeah, so in all three directions. So it's similar to find a difference. We need some overlapping, but near the boundary, near the Dirichlet boundary, we don't need any overlap. So now, when you have a hybrid method, okay, so we know method typically an order of magnitude more expensive than a linear method. So in a parallel implementation is not completely load balanced, because you got the Reno methods, the subdomains with Reno methods that they take longer. Okay, it's not completely load balanced, but it's still it is faster than pure Reno solver. Imagine that you have a bunch of subdomains for each processor, and then let's say out of that bunch of subdomain, there's a portion of Reno, and the rest are FC. So it's still faster than pure Reno, and it is more accurate than pure Reno in the smooth regions. And we've shown that in 1D, 2D, and previous works, and I'm going to show you here also in the 3D. So this is a Taylor-Green vortex problem for verification, Mach 0.1, Reynolds number 100, and a specific heat ratio of 1.1. Velocity and pressures are sinusoidal, and these are the vorticity contours at t equals 0 and t equals 10. So as time passes, we got a smaller and a smaller scale, higher gradients, and this is the kinetic energy dissipation rate versus dimensionless time. This is very close to the results of other published data. So here, the other problem that I did is isotropic turbulence with eddy shocklets, turbulent Mach number of 0.6, Taylor scale Reynolds number of 100, okay? And the initial velocity field we're required to satisfy this energy spectrum, exponential, and K0 is the wave number with the highest energy. So what we plotted is dimensionless second order invariant of velocity gradient tensor. So this velocity gradient tensor is something like vorticity, okay? So this is at dimensionless time of 4, and on a grid 256 to the power 3, and we use 256 processor. You see the worm-like structure that we expect after the evolution of the random field, and start generating the smaller scale. And here we did a comparison of three methods. So the black line is for the fine solution, okay? is 256 to the power 3. Then we got red, green, and blue. Those are correspond to pure, we know, at a coarser level. CD, we know, central difference, we know, and the blue is FC, we know, on a coarser. And you clearly see that the pure we know on a coarser grid is not as accurate as the other two, because compare the red line with the, let's say, black, and compare that with the blue and green. So you see they're significantly lower. Then if you compare green and blue, which is what? Which is the CD we know and FC we know, you clearly see that this region here, the CD we know, FC we know, is much closer to the fine solution. So if you go to look at the dimensionless entropy, you see similar behavior. And again, if you look at the green, blue, and which is for CD and FC, we know, and compare it with the black again, you see that after the peak, the blue is closer to the black, okay, and the pure we know is highly dissipated. So, not sure you can see the values on this table, but I tried to quantify the errors. Let's just, yeah, so you clearly see that the pure we know, the coarse we know, has 7% error, let's say, in entropy. Then CD6 we know 9 is 4% error, and FC we know is 2.8% error. And on the second column from right-hand side, you have the we know fraction, is the number of subdomains that are average over time, and space that are used for we know. So for CD is 3%, CD we know 3%, FC we know 3%. So the 97% are the smooth solvers. Only a small percentage are we know, and we have a speed up of roughly 3 over we know method. And so conclusion, FC Vino is a high-order efficient scheme for complex flow problem with both a smooth and discontinuous solution. Extension to turbulent and multi-phase flows are ongoing. And I would like to thank Dr. Lasani. Discussion on the turbulence structure, and also the runs are done on our high-performance computing cluster at STSMT. Thank you very much. If you have any questions. Yes.
Very impressive. I just have a question. Slide number 7.
Slide number 7. Yeah. Yeah.
Yeah. Here, actually, you do some sort of mean-going extend the interval to actually impose non-periodic. I was curious why you didn't use Chebyshev polynomial.
Oh, okay. It's a very good question. The Chebyshev polynomial.
And you can still use FFT. Sorry for interrupting. You can still use FFT to do Chebyshev.
No. I mean, it's a very good point. Actually, people use that in a context of even hybrid method Chebyshev polynomial. There's two scales and n squared. Okay. Here, because you got equi-spaced, is n, okay? That's one thing. The other thing, you have we know, which is a uniform grid, Chebyshev, which is non-uniform, then you need to do what? You need to do interpolation. In fact, Weiss-on Don at Brown and collaborator, they actually implemented that. I believe they didn't get any advantage of using just pure Reno because the overhead is too much, CFL condition is restricted. So this one, we've shown that it's actually more beneficial. Any other question?
Thank you.
Open? Yes, question.
Sorry. Just in the boundary.
Yeah.
Does the FC method active in the boundary? Does it go backwards in domain to look for the neighboring inclination?
For the FC Wiener method, FC Wiener method is requires overlap. It's not like Chebyshev method, let's say, that what you need is just a continuity at the interface. So here you step to the neighboring, typically 3 grid points. For stability, you need some overlap. It's like find a difference.
Yeah.
You need some overlap.
Because the wind scheme, you just when you build a high order polynomial, you need the degrees of freedom for the extensive right?
Yeah.
When you're in the boundary, the stencil just shifts backwards, for instance.
Yeah. Oh, if you are at the boundary, physical boundary, you don't need extra point for FC Wiener method. For interior boundary, you need overlap. Yes. Yeah. Yeah.
So it's more efficient.
Yes. At the boundary, you can get fifth order active.
Yeah.
So if you only use Wiener method, pure Wiener method at the boundary, you get what second order method, and you can't even go higher than that. So find a difference, become unstable of second order. So you could go at the boundary, fifth order.
And if I may,
Yeah.
do you see any issues going to unstructured grids or
unobstructed grid? Okay, so if you're going to tetrahedron, I don't know how to do it. Tetrahedron, I haven't figured out how to do it. But if you go with structure hexes that are deformed, yes, it is doable, because you can do it through a mapping. Yeah. You could do it through mapping. So you get you got a curvilinear domain. Okay, you can always map it to the Cartesian. So you can do that. But when you're talking about unstructured hex, really unstructured hex, and then TED, it's not doable. So what people do, like I think Oscar Bruno's student, one of his students was doing to use these patches, big patches that are curvilinear. And then you have to do the interpolation of data, which for nonlinear problem you may have to solve a Newton method for that mapping. So it gets more complicated. Okay, thank you.
Thank you.
So next up we have Jung, who is a second-year PhD student at George Washington University, and he'll be presenting on, I guess I'll let him say that.
Yeah. Good afternoon, everybody. Today I will present my research work. The title is High-Order Vector Difference Method for Fluid Structure Interaction using an implicit-explicit archive-covering scheme. So I will talk about this research in the following 5 sections. So let's just start with the motivation. Over the last decade, many numerical approaches for fluid structure interaction have been applied to a wide range of engineering problems. For example, the flapping flight and the blood flow in the cardiovascular system. However, the problem is that most of them are up to only second-order accuracy, just like the previous talked about. The high-order method is much more efficient and can get much more accurate results. So for the low-order accuracy method, it is inadequate for simulating unsteady vortex-dominated flows and the turbulence for aeroelasticity. So in this research, we just propose to develop some high-order numerical methods in both time and space for FSI problems. So far, we only consider the invested fluid. The invested fluid is governed by the Eulerian equations. It can be written in equation 1. It can be written in equation 1 on the physics domain. And right here, the QF is the conservative variables, and the F and G is the invested flux. If we use some analytical isoperimetric mapping, then we can get the non-conservative Eulerian equations on computational domain right here. So the last three terms is the non-conservative terms. Basically, if the mapping is isoperimetric, and we can also specify the velocity and the position of the mesh in some analytical expression, then the non-conservative terms will vanish. But for our cases, we use the analytic isoperimetric mapping, so the G2 and the G3 will be 0. But in some cases, with the mesh deformation and the mesh velocity and mesh position might not be very consistent with each other. So in that case, the G1, this term, they might be non-zero term. So we cannot just remove this term from the non-conservative equations. Therefore, the equation 2 can be reduced into the equation 4 with the non-conservative term. If we rearrange this equation 4, then we can get the final governing equations for our cases. Right here on the right-hand side, the last term right here is, we can treat this as a source term added into the governing equations. So if the mesh is stationary, therefore the source term will be 0. Then we can get the conservative equations on computational domain. But if the mesh is deforming, and in some cases the mesh velocity and mesh position is not consistent with each other, this term will be non-zero term. So actually, there are two types of methods to add this source term. One is that in equation 5, we just add this source term into the continuous governing equations. Let's say this is let's just call this implementation G01. Another way is to add this source term into the discrete governing equation. Here we call it the G02. For the structure model, we only consider the one-dimensional harmonic oscillator. It's governed by equation 6. Here, D is the displacement, and M is the mass. D double dot is the acceleration. Ft is the external force. By introducing the solution vector, let's say the Qs, we can rewrite the governing equation in equation 6 as equation 7. So this is the final governing equation for the structural model. And also we employ the spectral difference method to describe our fluid governing equations. This plot just shows one standard cell for the SD method. In the SD method, we employ two sets of points, namely the flux points and the solution points. Right here, the red square is the flux point, and the blue circle is the solution point. Both of the flux and the solution in SD method are interpolated by the tensor product of the Lagrangian polynomial right here. And because this polynomial is just cellwise continuous, it means that at the interface, the flux is discontinuous. So in this case, we use the Riemann solver to compute the continuous flux at the interface. And for the fluid and the structure, here we employ the Astor scheme. It's called the explicit first stage singly diagonal implicit Runge-Kutta method. This is the virtual tableau for k-stage Astor scheme. For the Astor scheme, the first stage is explicit, and the rest of the stages are implicit. And also, the coefficients located at the arc triangle, they are 0. And the diagonal coefficient for each implicit stage is the same. Using the Astor scheme, for each implicit stage, we will get one implicit system. So here we just use the aerial symmetric Gauss-Seidel or aerial SGS method to solve this linear implicit system iteratively. And for the coupling, here we just want to use the implicit explicit arcade coupling scheme to couple our fluid solver and structure solver together. This coupling scheme works in a partition method. Let's say we already have a fluid solver and we already have a structure solver. We want to couple these two solvers together. So this scheme just transfer the information as the shared boundary of the fluid and the structure. So it's very convenient because we can apply this scheme to the already existing fluid solver and the structure solver. And so in this scheme, the traction term from the fluid to structure is integrated using some explicit Archimedes method, and the remaining terms will be integrated by the Astor scheme. Actually, this implicit explicit Archimedes method is also called the additive Archimedes method. It is initially used to the advection, reaction, and diffusion problems, because in that kind of problems, the time scales of reaction is very small compared to the diffusion or advection. So for that kind of problems, because implicit Archimedes method doesn't have the stability issues, so in that kind of problems, they just the reaction term is integrated by the implicit Archimedes method, and the advection and the diffusion term will be integrated using the explicit method. Here we just adopt the same idea right here. So for each implicit stage, first of all, we need to predict the traction term at this time stage. By this, the traction term is interpolated by the ones from the previous stages, and then once we got the predicted traction term, we can use the T tilde n plus Ci to solve the structure implicit system at this time stage. Once we get the Qs n plus Ci, then we can update the whole mesh in the fluid domain, and then we can. This one is already known, so we can just use this Qs n plus Ci to to solve the fluid implicit system. And then once the fluid system is solved, we can actually calculate the actual traction term at this time stage. After the actual traction term is obtained, we will re-evaluate the structural residue, because right here we use the predicted traction term. So once this term is obtained, we will re-evaluate the structural residue. So after all this process, we can advance the structure and the fluid to the next time level. First of all, we just test our fluid solver using the 1D free stream test case. This test case is trying to test the effect of the source term. These two plots just shows that here we use two types of implicit methods. One is the multi-step method. It's called the BDF2, the backward difference formula. And another one is the ASTERK. It's the multi-stage implicit method. From these two plots, we can see that after we just add the source term into the governing equations, so the error is significantly reduced, which means that after adding the source term, the free stream can be preserved very well, both for the JCL1 and the JCL2. So because the JCL1 is with the continuous source term and JCL2 with the discrete source term. And then we test the JCL1 and JCL2 using the 1D wave propagation test case. The left plot just shows the result solved by the BDF2. So we can see that both of the JCL1 and JCL2 can achieve the designed time accuracy of the BDF2. But if we look at the right plot, we will find that the JCL2, the time accuracy of the JCL2 is reduced to only first order, even though we are using third order ASTERK schemes. But the JCL1 can preserve the designed time accuracy, which just indicates that the JCL1 can be widely applied. The JCL1 can be widely applied and work very well for both the multi-step and the multi-stage implicit method. So here we employ the JCL1 for our FSI framework. And we further test our JCL1 scheme using the two-dimensional Euler vortex test case. So the Euler vortex, this is the invested Euler vortex. This vortex is propagating from the left to the right, and the boundary is the periodic boundary conditions. We tested the time accuracy by using the JCL1 scheme. The left plot is for the BDF2 scheme, and the right is for ASTERK scheme. So we can see that both of the BDF2 and the ASTERK scheme. So we can see that we can see that the JCL1 scheme can preserve the designed time accuracy both for the BDF2 and the ASTERK. And then finally, we test our FSI framework by using the one-dimensional piston problem. Actually, this is a linear piston problem. So the cylinder is filled with gas, and this is a piston attached with some linear spring. So the piston actually will move back and forth periodically. So this test case, we have the analytic solution, and we test the FSI framework. This is the calculated temporal order by using our FSI framework. We can see that both for both second and third MX methods, our framework, our FSI framework can achieve the design time accuracy. So then the summary is that, okay, first of all, we have developed a novel high-order accurate computation framework for FSI problems by using the IMAX SD covering scheme. And we also demonstrated that the JCL1 with continuous source term can be applied to both implicit multi-step and multi-stage schemes, while the JCL2 with the discrete source term failed in multi-stage time matching method. And third, we verified the high-order accuracy of the FSI framework through the 1D precedent test case. So the future work will be to extend this framework to 2D and 3D, and also add the nonlinear structure solver into our framework. Thank you.
Do we have any questions?
If I may. Any particular reason for choosing the spectral difference method over DG or some other higher method?
Because first of all, the spectral difference method is using the differential form of the Gaussian equation, and the DG is using the integral form. But so one advantage of the SD method is that it doesn't involve the the numerical integral, so it will be much more efficient. And another reason is that from some published paper, it reported that the spectral difference method can be much more stable than the DG method. And also, we can use much larger CFL number for SD method. So that's why we choose the spectral difference method. Yeah. Okay, thank you.
Well, I'm sorry, I had a question.
Okay.
What do you see as sort of the next steps of the method? So it seems like you've developed it, you've proven that it works for an analytical test case. Do you foresee what your next steps would be with the method? Do you have certain physical problems you're interested in? Or?
Yeah, exactly. We just for this kind of work, we just demonstrate that this method just works.
Sure.
So the next step will be extending this method to 2D and 3D, and also right now we are just dealing with the linear piston problems.
Yeah.
So we want to add the nonlinear structure solver into this framework, so we can just do some real world applications. Yeah.
Cool. Any other questions? Okay. Well, thank you very much. So that concludes our session for today. Any of the people that have presented, I don't know if you saw my laptop over there, but I've recorded the thing so I can either one of us can swap information if you'd like a link or a copy or anything like that. So otherwise, thank you very much for everybody coming.